So today we're going to solve the following integral. I is equal to the integral from 0 to 1 of x times the ceiling function of 1 over x dx. And so the first thing we're going to do is set up an inequality. N minus 1 is less than 1 over x, which is less than or equal to n because of the ceiling function. And then next, we're going to invert everything and we'll get 1 over n is less than or equal to x, which is less than 1 over n minus 1. Next, I'm just going to plug in a few values for n. So for n equals, oh wait, notice n cannot be equal to 0 or 1. Next, if n equals 2, then we get 1 is less than 1 over x, which is less than or equal to 2, which means that 1 over x is equal to 2 because of the ceiling function. And if we look at our other inequality, x is going to be in the interval 1/2 to 1. And notice how we want to integrate from 0 to 1, so this will be our first, I guess, integral bounds whenever we break up the integral. So next, n equals 3, we get 2 is less than 1 over x is less than or equal to 3, which means that 1 over x is equal to 3. And this pattern, and that also means that x is in 1/3 to 1/2, just based on this up here. Then this rule holds for all n. So for all n not equal to 0 or 1, such that x is in the interval 1 over n to 1 over n minus 1, 1 over x is equal to n. I don't know if that makes sense, but we can see here 1 over x is equal to n. So now our integral is going to be equal to the sum from n equals 2 to infinity, the integral of 1 over n to 1 over n minus 1 of x times n dx. So we can integrate this really easily because I is equal to the sum from n equals 2 to infinity of n times 1/2 x squared from 1 over n to 1 over n minus 1. Means we have, I'm actually going to switch colors here. We have I is equal to the sum from n equals 2 to infinity of n over 2 times 1 over n minus 1 squared minus 1 over n squared. And then we want to simplify this. stuff in the parentheses. So 1 over n minus 1 squared minus 1 over n squared is equal to, let's see, a common denominator, n squared minus n minus 1 squared all over n squared times n minus 1 squared. And then expanding the brackets, you get n squared minus n squared minus, plus 2n plus 1. So those go to 0. Then you're dividing by n squared times n minus 1 squared. And then if we go and plug that back into the sum, we get hold on. So implies we get I is equal to the sum from n equals 2 to infinity of n over 2 times 2n plus 1 all over n squared times n minus 1 squared, which is equal to the sum from n equals 2 to infinity of these n's cancel out, so we get, I'm going to pull that 1/2 out, so hold on, here we go, 1/2, 2n plus 1 all over n times n minus 1 squared. Okay, so now we're going to do some partial fraction decomposition. So PFD. So we want to break up 2n plus 1 all over n times n minus 1 squared, a over n plus over n minus 1 plus c over n minus 1 squared. Okay. And then for the common denominator is going to be n times n minus 1 squared. So we get 2n plus 1 is equal to a times n minus 1 squared plus b times n times n minus 1 plus c times n. And now we set n equal to 0, which means that, n equal to 1, which makes this a part 0 and this b part 0, so we get this is 2n minus 1. We get 1 is equal to c. I'll write that better. This implies the 1 is equal to c. Now, for n equals 0, we get a equals -1. Oh my gosh. And then you can just plug it back in. So now we have 2n minus 1 is equal to -n minus 1 squared plus b times n minus 1 plus n. Subtract n from both sides. We get n minus 1 is equal to negative n minus 1 squared plus bn times n minus 1. And then you can see you can divide out by n minus 1. And that gives you 1 is equal to bn minus n minus 1. Right? Because cancel that out. Yeah. So now we have 1 which also equals bn minus n plus 1. Subtract 1 from both sides. You get 0 is equal to bn minus n, which means that you get b is equal to 1. So we have a is equal to minus 1, c is equal to 1, and b is equal to 1. Okay, so now we take this equation, move it down here. Okay, okay, so we get minus 1 over n plus 1 over n minus 1 plus 1 over n minus 1 squared. And then obviously we can plug that back into our integral, or our sum. So I'm gonna change colors, this one. So this implies that I is equal to the 1/2 times the sum, it's terrible, sum from n equals 2 to infinity. We want to rearrange these terms, telescoping, so we get 1 over n minus 1 minus 1 over n plus 1 over n minus 1 squared. And obviously, we can break up this sum into two different sums and evaluate them separately. So we get 1/2 times the sum of, gosh, terrible, n equals 2 to infinity of 1 over n minus 1 minus 1 over n plus the sum from n equals 2 to infinity of 1 over n minus 1 squared. Okay. So, we'll take a look at this first sum and call this I sub 1, and the second one will be I sub 2. So now we have I is equal to 1/2 times I sub 1 plus I sub 2. Okay, so for I sub 1, we have, I'm going to actually delete this and say for I sub 1, we have the sum from n equals 2 to infinity of 1 over n minus 1 minus 1 over n. And I'm just going to start writing out terms for it. So if we plug in 2, we get 1 over 1. So that's 1 minus 1/2 plus, plug in 3, we get 1/2 minus 1/3. Plug in 4, we get 1/3 minus 1/4. And that keeps going on. And obviously you can see that these all cancel out. And this is just equal to 1. So I sub 1 is equal to 1. And then for I sub 2, we have the sum from n equals 2 to infinity of 1 over n minus 1 squared. And what I'm going to do is say k is equal to, wait, no, sorry. N is equal to k plus 1, which implies that I sub 2 is equal to the sum, man, that's terrible, sum from k plus 1 equals 2 to infinity of 1 over k plus 1 minus 1, minus 1 squared. And obviously these go to 0, and then we'll get I sub 2 is equal to the sum from k equals 1 to infinity, just by moving this 1 over to the other side here. And we'll get 1 over k squared, which is well known. This is the Basel problem. This is pi squared over 6. So we know that I sub 2 is equal to pi squared over 6. I sub 1 is equal to 1. So we have we have I is equal to 1/2 times 1 plus pi squared over 6, which is equal to 1/2 plus pi squared over 12. And that is our final solution for this pretty cool looking integral. It was the daily hard integral today, so I thought I'd make a cool short video over it. It's pretty interesting. But yeah, that's all for now. Thank you for watching.